Okay, this problem is going to have an old familiar feel to it because you're going to be recognizing that we're dealing with a piecewise function, which we definitely dealt with in our first chapter when we were talking about continuity. So big key concept there to keep in mind. And now we're going to be looking at differentiability. So we're not actually going to look at tangent lines in this video, but definitely continuity and differentiability. So the ultimate question I'm asking, I know I broke it into an A and B here, but the ultimate question I'm asking is, what would A and B have to be in order to make the function, the piecewise function f of x, differentiable? Okay, and because we have that requirement that in order to be differentiable, it must be continuous, that's actually going to help us out here and allow us to get a second equation so that we can then solve for two variables at the same time. So I'm going to do a quick little sketch over here to the side because sometimes I like to just think things through before I jump in and do the math. Or maybe we'll actually go up here. We're going to do, I know that first function, that one's defined as 3 minus x. So I'm going to think of that as negative x plus 3. And if I'm thinking of y equals negative x plus 3, well, I've got a 1, 2, 3, and I've got a slope of negative 1. So my line looks something like this. And that's for x is less than 1. So I guess I did that too far. Let's erase part of this. And let's say that's for x is less than 1. So that part of my graph. So here's what I need to make happen. I know my other one is a parabola, and I know it's opening up. So that's pretty cool. I can kind of picture my parabola moving around. But I want to make that parabola not only start right here so that 1, 2 is an actual point on the graph, but I also need to make it so that it doesn't do something like this, or it doesn't do something like, let's see, here's some other options. It could be that my vertex is over on the left somewhere, and it's going like this, and then I create that corner on my graph. So I don't want any of those to happen. What I want to happen is I want it to be something where it just smoothly goes from straight line to parabola so that the slope at that point 1, 2, that's the point I'm worried about, is exactly the same when I come off my line and start my parabola, because we know on the parabola the slopes can be changing at every point. So just that very one instant I need it to be the same. So here's the calculus that's going to help me to accomplish that. We'll keep that picture kind of, maybe I can just, oh, come on, picture, shrink. There we go. We'll keep that in the corner, just my thought picture. And let's go ahead and see what we can do with some calculus and some notation here. If the function is continuous at x equals 1, what is the relationship between a and b? Explain your reasoning using limits, our favorite. Let's do it. So if I'm using limits, then I know that basically the functional value from the left side has to equal the functional value from the right side. But because my function isn't defined for the first piece, when x is equal to 1, I have to use a limit to express that. So the limit as x is approaching 1 from the left of my function has to equal the limit as x is approaching 1 from the right of my function. And then, of course, the limit has to equal the functional value, but I'm kind of taking a shortcut here with my continuity definition because I know that for the second piece, my function is defined exactly where the limit is going to be because I don't have a rational function here. I'm not worried about any asymptotes. So once I actually make the limit exist, I know the functional value will be the same and we'll be good to go. So plugging into this, I'm going to take my first piece, 3 minus x, and I'm going to say 3 minus substitute in. So the piece that I just used here for my f of x was my first piece. And then for my f of x here, I'm going to use the second piece. So I'm going to say 3 minus 1. Again, we evaluate a limit by substituting in this value in for my f of x, and since that was 3 minus x, that's why I put the 1 in. 3 minus 1 has to equal a x squared, but my x is 1, plus b times x, and again my x is 1. So take a look at that equation, make sure you're okay with that. And if you're good with that, then all we're going to do is tidy that up. And we're going to say that we have 2 on the left is equal to a, because 1 squared is 1. So I've got 1a plus 1b. That's a nice simple equation for us to work with. Okay, so let's just leave that one alone for a second. I'm going to go ahead and put a little box around it just so I know I'm not done with it, but just so I can come back and find it. I can't do anything else with that until I've got a second equation, because I've got 2 variables, 2 unknowns. So I either need to solve for one variable using a different equation that only has one variable, and then come back and substitute it in, or I need to make a system of equations. So let's go over to B here. B is telling me to find the unique values of A and B that will make F both continuous and differentiable at x equals 1. Write another equation is my hint to you. So my first equation, recall, was all about the function being continuous. All we did right there, going back to my picture up here, is we made it so that we filled the hole in when I changed from line to parabola. So now what I want to do is I want to make it so that the slopes are the same. And when I'm talking about slopes in calculus, what am I talking about? You got it. I'm talking about derivatives. So what I need to do, and I'm going to try to write this for you as clearly as I can. What I need to do is I need to make the derivative on the left side, so that would be of my function 3 minus x, equal to the derivative on the right side, which is my ax squared plus bx. So I'm using a different notation for derivative than I normally use because it allows me to put in parentheses after it what my function is. The d dx is noting that I'm going to take the derivative. I have not yet taken the derivative of that function. So, and then of course I really only care about at x equals 1. So I'm going to go ahead and write the derivative as a function, and then I will substitute in. So as a function, the derivative on the left would be, now I'm going to actually differentiate. On the left it would be a negative 1. I'm getting that from my negative 1x, so my power rule. Derivative of 3 is 0, so the 3 goes away. And then on the right hand side, derivative of ax squared, drop the power down, would be 2ax to the first, plus derivative of bx would be bx to the 0, so the x goes away. And that's my general derivative function. But of course I'm really only concerned about at x equals 1, because clearly the derivative of the parabola is changing. Derivative is never the same here, and the derivative of the line is actually always the same, and that's what we've established so far, is that's negative 1. You could have told me that before you entered calculus class. That's based on my y equals mx plus b. So I'm going to substitute in for my x value a 1 right here, because I want to know when x is equal to 1, and I'm going to rewrite, and I've got negative 1 is equal to 2 times a times 1 plus b. In other words, negative 1 is equal to 2a plus b. And it looks like we have ourselves a second equation that has both an a and a b in it. And at this point, the calculus is done, folks. Now you're into algebra mode, and you're looking at, I've got a system of 2 equations with 2 variables. There's one, there's the other. You go for it, whatever method you like for solving a system of equations. My recommendation is always use elimination, unless there's absolutely a very good reason that you can't. So I would be doing elimination right now to go ahead and solve for my a and b. I think that gets you to where you need to be. I would recommend you plug in a and b at the end and make sense of your answer. Do a quick check. Go back to our picture up here and make sure that it makes sense with our picture. Just go ahead and actually find that value and go ahead and actually find that slope. Good luck.